Hello again. Time for another one of these requested, could I do some revision of a particular thing? I was asked about 3D drawing, but that kind of has to be done in connection with EPRT, as I call it. You find it written in various other sources as VEPRT, the V standing for valence. I just think about it, you just need to think about pairs of electrons. So it's electron pair repulsion theory. So it is just about electrons. I'm not going to write out what that stands for, it'll take me too long, but electron pair repulsion theory. Alright, and it is just two electrons, that's a pair, they're negative. They will repel other pairs of electrons, and they repel them as far away as possible. So the whole point of that is negative electrons repel each other to furthest, I can say distance, but it's probably not the right word. It's what it does is it repels them around the centre of the molecule until they're as far away from each other as possible. So it dictates from how many pairs of electrons are pushing each other round the molecule centre, the shape. We'll come to the shapes in a moment. There's this other thing where we need to remember the 2.5 degrees. 2.5 degrees is the extra repulsion you get from a lone pair. Now if you talk to somebody who's a little bit more further into chemistry, they'll say, oh, that's a bit rough and ready. But for A level, that's enough. So a lone pair, 2.5 degrees. So what a lone pair does, because it's not bonding to an atom at the other end of the lone pair, what happens is it's slightly more in towards the nuclear, the central atom, the centre of the molecule. And therefore it's more concentrated, so it pushes with more repulsion the bonding pairs away. So if you've got one lone pair, it closes the bond angle by 2.5 degrees. If you've got two lone pairs, it closes it by 5. You can't have 3 lone pairs on the majority of shapes unless you're down here. So we don't tend to think about 3. So the shape of a molecule is dictated by the number of pairs of electrons. There are more than 8 shapes. Don't actually know how many there are, but at A level there are 8. I had to have a cough. There we go. I could feel it coming in that other sentence. Now you need to know the 8 shapes. Some of those 8 shapes I have not got some horrendous disease that we're all talking about. Oh. Well, we had to have a little break there, we had a little bit of a cough there. Now I have to go and get a drink. So, 8 shapes. Some of them don't need a 3-dimensional drawing. Some of them you can do it with 3D, not with 3D. But some of them you do need a 3D. I'm not going to draw them out right now. I'm going to do that a little bit later. Just going to list them off. You might want to get a piece of paper. You might want to pause the video if you haven't got a bit of paper and make some notes as we go along with this, because this is the kind of thing that you need to do. So, only one shape for 2. This is, perhaps I should have said, that's the number of electron pairs so that's not right. That's the number of bonding pairs. Bonding pairs. So when there are 2 bonding pairs, they just push each other away. You get 3 atoms in a straight line around that centre one. Lydia is the name. When you get 3 bonding pairs, you have Trigonal Planar. This is one of the ones that you tend not to bother with. These are the 2 that don't bother with a 3D drawing. And there was only a single one for 3 bonding pairs. When you get to 4 pairs, The 4 bonding pair one is tetrahedral. But what also happens is that you then get a modification of the shape when you start bringing in lone pairs. So you get 1 lone pair and the 2 lone pair. I'm not sure you can read that, might be a bit small, but 1 lone pair up there, 1 lone pair, Trigonal Pyramidal. The lone pair, most people view it like me at the top, and it pushes the other 3 down below the central atom where the lone pair is as well. You get a thing called Trigonal Pyramidal. It's not like a proper pyramid, it's quite a squashed pyramid, as we will see when we do the drawings shortly. 2 lone pairs, it comes in 2 names. The name that most people use, I think, is bent. But you also see that called V-shaped. I tend to call it bent because it's a shorter word. Right, 5 bonding pairs. Now 5 bonding pairs, this is one of the ones where there's additional shapes to outside of A level, but the one that you get is, because you only ever get one example at A level that seems to crop up for this. So oh dear, forward planning, run out of board. There we go, Trigonal Bi-Pyramidal. And then
once you get to
6. So I was just having a count up there thinking I ain't got enough. The standard one is octahedral, but there's a modification of it when you have usually 2 lone pairs. That modifies it to become square planar. That's a simplification of that, because there are other ways you can do that, but one of the things to consider is that you get square planar. Square planar is the 8th shape at A level. Tends to crop up a bit more in year 13 when you start talking about transition metals, but that's a little early because we're here for year 12. So we have 8 shapes: linear, trigonal planar, tetrahedral, modified into trigonal pyramidal and V-shaped or bent, Trigonal Bi-Pyramidal, octahedral and its modification of square planar, which is obviously, that list has upset my hands because I can hear them through the window. I will see you after the edit because I need to wipe the board and get ready for 3D drawings and other drawings that are not 3D. See you in a moment. So, 2 shapes first of all. Linear. Linear, literally meaning, like I said just a little while ago, 3 in a line. Tend to see it in a couple of really common examples. The molecule, unexpected molecule in reality, beryllium chloride. There are no lone pairs around beryllium. It's only got 2 outer electrons, so therefore 1 in each one. So it does mean that dot and cross diagrams play a role in determining this, because the dot and cross diagram, which is not in the scope of what I'm doing in this video, allows you to determine if there are lone pairs, and therefore you need to consider them in determining the shape and then the drawing that you have to make. Beryllium, no lone pairs, so just 2 bonding pairs in a molecule, straight line, 180 degrees. You are expected to be able to state angles, and there's a little bit of memory about some of the angles, well, one in particular, and that's one example. The other one is a much more common thing, which carbon dioxide, linear. two double bonds, they're just pushed away from each other. You can think of it like that. That's not necessarily the way it's explained at university, but 180 degrees again, same thing, 180 around there. Now, Trigonal Planar is when, again, you don't have a lone pair doing any manipulation of the shape. Two obvious examples. There is a set of things based around boron, not just the fluoride, but boron trifluoride is one of them. Boron, with the number of electrons it's got, means that when you do its dot and cross diagram, it doesn't have any electrons left for a lone pair. It only has 3 outer electrons. They're all used up in the bonding with the fluorines. So there's no lone pair. So there's nothing other than 3 things getting as far enough away from each other as possible, and the bond angle therefore is 120 degrees. The other example, which is technically not 120 but it's very close to 120, is when you're in an alkene. So when you're in an alkene, the carbon with a double bond on it, 3 directions, no more electrons making lone pairs, so therefore you're looking at 120 degrees. The reality is that this is slightly more repulsive to these and you get a slight change, but at A level we don't tend to get upset about that. So these are all 120 approximately, shall we say. And so that then goes on into the rest of the alkene. You could do it with, there would obviously be another carbon on the end of that double bond. You could just make it ethene and everything is 120 degrees in ethene, or you could make it goes on to be propene and it's all 120 degrees around the second carbon. But not this one, because this one's coming up after I've wiped the board. And we'll be into the next things, the tetrahedrals. So, tetrahedral, really common thing in the 3-dimensional drawing thing at A level. So, tetrahedral, a couple of things you need to remember about tetrahedral. Firstly is that it has a bond angle that you need to remember. So, that number that you need to remember for 2 reasons. 1, because you need to remember it, and 2, because you need to modify it when you start talking about lone pairs. 109.5 degrees, give or take a little tiny bit. So, 109.5 degrees. You need to remember that. Can't say I can draw 109.5 degrees, you can just do the 3-dimensional close enough drawing to it. Now, starting position would be methane. Now, methane in a displayed formula, which looks like that, does not tell you the shape of that molecule. It is not a rolled flat by, not been splatted flat. It's not like that. Displayed formulae are a convenience in order to identify what bonds you've got. They are not a representation of the shape of the molecule, because those are 90 degrees away from each other and you can get them further away from each other. You can get them to 109.5 degrees, and 90 is obviously nowhere close to 109.5. This is where 3D drawing comes in, and this is what someone was asking me about. 3D drawings with tetrahedral, you have to think of the surface that you're drawing on, it's called the plane of the molecule, that the surface you're drawing on, and then you can go out in front of the surface, in front of my board, and you can go behind my board, but you can't physically do that. You can do that with a 3D clip together model kit, but we're trying to be able to represent 3 dimensions on a flat piece of paper. So what you have to think with tetrahedral is there's a central atom. I've done it very big. There's a central atom, and you need to draw 2 bonds in the plane of the molecule or the plane of the paper. I'm doing methane, so these will be hydrogens. If you can't see that, you need to get yourself a new computer. So then the other 2, one of them comes out in front of the plane of the paper or the surface, the other one goes behind, and you represent that by doing that for coming out towards you. Oh, there's another one of the lights, motorbikes going past outside. And to go behind the board, you kind of flip that round the other way, but don't do it as a triangle. You do it as ever decreasing vertical lines, and then you get a hydrogen. I've done my classic, it's away from you, it's further away, it's a little smaller. Don't tend to see that in real drawings. But so therefore that is a representation of 3 dimensions. I probably could have done it better, that could probably have been round a bit, but it'll get you the marks in an exam, no problem for doing something like that. So that angle there is the 109.5 degrees, as is that angle there, that angle there, that angle there. All of the angles are 109.5 degrees. It's a completely symmetrical molecule with 109.5 degrees between any 2 bonding pairs. So that's the basis for tetrahedral drawings that you then modify. So the thing about the 3D, 2 in the plane, and then 1 with a shallow triangle coming out towards you, and the other one in a load of dashed lines fading away into the distance, is the behind. And we'll continue with that as a representation in the other shapes. I'll see you after the edit when we'll do the what lone pairs do to tetrahedral. See you in a moment. Modifications of the tetrahedral: Trigonal Pyramidal, 1 lone pair as the modifier. Here, 2 lone pairs. Examples of that molecule: anything in group 5. Standard one that you see, NH3, could go down an element, PH3, could go PCl3, NF3. They're all modified in the same way by 1 lone pair. So when you need the dot and cross diagram to identify there's a lone pair. Like I said, we're not going to be doing dot and cross in this. So you have got a lone pair on the nitrogen in lieu of a bonding pair, but slightly more repulsive. So you could think of it in any way, because you can rotate the molecule, but you kind of need a way that you can remember, I think, to draw it. So start with the nitrogen, and I would say 1 lone pair sticking up the top. That forces you to have had one of the in the plane positions taken by the lone pair. So then 1 bond to a hydrogen in the plane. That then means that to complete the drawing, you would have 1 out, 1 behind, and therefore you have that. Some people say, do you have to do these on the left hand side? No, you can flip the whole thing round and do the bond. This bond can be over there. Just do the whole thing in reverse. I just happen to have done it the same side each time. When you get to this one, group 6 is the classic thing, oxygen, sulfur. So standard drawing expected comes from water, but H2S is the same. 2 lone pairs. Now, what do you do with 2 lone pairs? Well, you can think of it in 2 ways. You could do you can put the lone pairs in the plane that you're drawing. That then means that that comes out there and that goes away there. We'll come to the bond angle thing in just a moment, in case you're thinking he's forgotten the bond angle. The other way is to put the oxygen in the middle and go, put the 2 hydrogens in the plane. I suppose you could go in between and do one, but it gets a bit messy when you do that. And that then means that you've got 2 lone pairs to consider. But you can't represent the lone pairs going in and out. But then you are only expected to really know that it's, 3 in a V shape. It's not really a V. That's why I don't like the word V shapes, can't just a bent thing. Now bond angles, base tetrahedral angle from before 109.5, one lone pair minus 2.5. So there is 107 degrees. We're getting to the end of my pen, I can see it coming, it's running out. So 2.5 degrees off, 107. So each one of those is 107. You don't do the identification of the angle between the lone pair and the bonding pair. You just look at the angle between actual atom centres. So when you do this, which I've now got two drawings in the way, let's get rid of this one, and oh, my surface is losing its smoothness. The same idea, 109.5 degrees, two lots of 2.5 is 5, take that off, 104.5 degrees. So that angle there, because it is only, remember, the angle between actual atomic centres that you look at, 104.5 degrees. Therefore, these are the two modified tetrahedral shapes. 2.5 degree modification for one lone pair, 5 degree modification for two lone pairs. Like I said, it doesn't have to be H2O. Something that's got two lone pairs is likely to be found in the group with oxygen and sulfur. Doesn't have to be hydrogen. Could be Cl2O. I'll see you after the break. See you in a minute. Well, had to change the pen. Hopefully, I think it was getting a bit of a struggle to read that. I hope you could read the last bits. The 5 bonding pair, Trigonal Bi-Pyramidal, tends to be the only example you find is PCl5 at A level. 2 bond angles to think about in this. I suppose 3, but 2 is enough. Now, it's quite difficult to visualise what this molecule would look like. You do the dot and cross diagram, you discover there are no lone pairs, that's one of the things. So, Trigonal Bi-Pyramidal, you've got an up and a down that is in the plane of the drawing surface. So, there it is. Then, you've got 3 left. So this is like linear. So they've gone linear up through that vertical axis of the molecule, probably is the right word. Then, round the centre you've got 3 without a lone pair. So that's going to be the Trigonal Planar. So you can put that one in the plane of the drawing surface. That then means that this one and that one are out in front and down behind. So when you look around the centre, these ones, 120 degrees each one, this is 120 here and 120 around the back. From here to there is exactly what it is there, it's 90 degrees, you can see it drawn as 90 degrees. You could also say, oh, that's 180, which is why I went, oh, there's 3, because you think about that as 180. But it's 90 degrees to the 3 that are around the centre, around the middle part of the molecule. So you get 2 bond angles to think about, 90 and 120, and then you'll draw it correctly. No lone pairs, so therefore it's Trigonal Bi-Pyramidal. And then you go, why is it Trigonal Bi-Pyramidal? Well, these 4 there make a triangular based pyramid. So when you look at those, this is where my artistic skills get a bit challenged. Triangular based pyramid, very poorly drawn, and then there's another one of these flipped over on the bottom. I think it's best I don't try and do artistic drawings because I've never been able to do them. So it is like a triangular based pyramid with another triangular based pyramid on the bottom, of which these chlorines are making the corners of the triangular base. That's PCl5. That just leaves us with the octahedron and the modification of octahedral. I'll see you in just a moment. Octahedral, some people have trouble identifying why it's called octahedral. It's because you look at the shape of the substance by looking at the external atoms and the three-dimensional shape that they make. You actually therefore don't include the central one in identifying the shape. Because otherwise people go, oh, it's got 6, why is it octahedral? Because the 6 points of the fluorines, in the case of SF6, if you were to join them all up and make them into a solid three-dimensional shape, would be one of those mathematical octahedrons. Now, got to get 6 in. So, same thing as before, an up and a down. Just like before, we do that, but now we need to do exactly that on the other side as well. So now you have 2 fluorines up above, 2 fluorines around behind, and 2 fluorines in the plane of the board here. If you were to join up all the F's, you would get an octahedron. When it comes to angles, well, because it's 4 around the centre, the furthest they can get away is 90 degrees. And from top to axial, round here as it is called, is also, I'll do it properly, with a mathematical rectangle. It's at 90 degrees also. Everything is 90 degrees in octahedral. Now, that's the three-dimensional drawing for that. The modification of that is when the central atom is not sulfur. The centre atom, that's one of those very special moments in chemistry where somebody discovered something that, oh my goodness, you can make a noble gas do some chemistry, is the compound xenon tetrafluoride. And here, there's a lone pair up and down, and that means that you've still got the 4 in a plane pushed by these 2 to be that square around the centre. So this is square planar. Okay. Now, like I said, there are some other modifications. One of the things you could do is you could say, oh, there's an isomer of this where you put, instead of the lone pairs top and bottom, you put one of the lone pairs instead of one of these fluorines and put a fluorine down the bottom, and then you get a, it's called a seesaw molecule. But we're not going to draw that on the board today. But you do get this isomer thing. Now when you're talking about octahedral and when you're talking about this also crops up in complex ions in year 13 with what are called ligands surrounding a transition metal. Quite often there are 6 like waters surrounding it, and that makes it octahedral. Sometimes there are 4, and it can either be tetrahedral or square planar depending on what you're doing. That's kind of it in terms of three-dimensional drawings of shapes. I'm hoping that I will have come up with some questions for you to practice on, and I'll see you for the next one of our revision videos when I've worked out which one it's going to be. Thank you very much. See you soon. Bye.